Hello. Today I will be examining how momentum transfers and art restoration methods use controlled impulses to remove dirt and grime from fine art safely. Specifically, I will explore how technology like laser ablation operates in order to ensure the preservation of the artwork. First, we will discuss the composition of the artwork and what must be removed. Then we'll look at the role impulse and momentum plays in the process, before finally diving into how laser ablation works and its effectiveness. Vincent van Gogh finished The Starry Night in 1889. If left untouched by conservators, however, what we would see today would be way different. Over more than a century, time would take its toll. This is due to both the natural aging of varnish and the introduction of surface grime. Varnish is a layer originally applied to saturate colors and protect the paint. Over time, though, because these are old varnishes, through cross-linking and oxidation, the organic material of the varnish slowly polymerizes, causing it to yellow and obscure the original work. Further, surface grime isn't just dust. Soot and modern pollutants penetrate the varnish and paint, becoming harmful inclusions locked within the very surface meant for protection. For a conservator, removing these compromised layers is critical to restoring the painting's intended aesthetic and to halt further deterioration. The traditional mechanical method used to remove varnish and surface grime is usually chemical solvents to dissolve or the use of scalpels to scrape it away. But these methods carry inherent risks, as the strong chemicals may penetrate into the underlying paint layers through cracks, or the mechanical removal of oxidized varnish may damage the original pigments. Therefore, the modern solution is the use of laser ablation for more precise removal working at a microscopic scale. Bare bones, laser ablation finds the exact energy impulse needed to separate unwanted material from the artwork. It delivers this precise pulse to the target layer alone. Shown here are the two most classic layers of removal. However, the interactions between the energy impulse and the layers targeted have a lot to do with the chemical components of the varnish and the surface grime. In this image, you can see the uneven makeup. Therefore, when deciding what wavelength or pulse time to use, it's not a simple case of where more energy means more cleaning. We will return to this concept later in the presentation. The core physics is seen by the impulse-momentum equation. Force multiplied by time equals mass multiplied by the change in velocity. Impulse equals the change in momentum. In classic examples, like car crashes or a bat hitting a baseball, we can observe this directly. A force applied over time interval causes a mass, the other car or the baseball, to change its velocity. This operates on a macroscopic level, a vastly larger scale than the laser cleaning of artworks. However, the same concept applies. The laser's energy delivers a precise microscopic force over a short time, providing the impulse needed to change the momentum of the debris particles and eject them from the surface. The system we are examining is the laser pulse in the surface material. This process is an inelastic collision, where kinetic energy is not conserved but is instead converted into other forms, such as heat and work. As the before diagram shows, a laser pulse delivers an impulse to the grime layer, for example. This impulse generates a force over the pulse duration, creating a change in momentum to a mass of debris. In the after portion, we can observe the result where the acquired momentum of the particle leads to the particle's ejection at a velocity, therefore successfully achieving selective ablation. This is an image of a simple apparatus for a pulsed laser ablation process, also known as PLA. We can see how the laser source generates the pulse onto the material. This apparatus creates a controlled, repeatable environment that is unlike the mechanical methods of conservation. This, for me, has been the most interesting part of this project. How do conservators decide what wavelength to hit the artwork with? These images are from a study of different wavelengths from infrared to ultraviolet applied to the black crust of sandstone. Conservators decide what wavelength to use by looking at the self-limiting effect. Self-limiting is when the laser stops at the level between the target and the original artwork, without damaging the underlying surface. This effect exists because the black crust in the sandstone absorb a specific wavelength of laser differently. Absorption depends on the chemical composition. Therefore, with paintings ranging in chemistry, it shows the critical nature of a precise calculation of wavelength in order for effective cleaning. The study's graph shows this difference by plotting the ablated weight on the y-axis against the fluence on the x-axis. For a wavelength like 1064 nanometers, shown on the upper right, the graph shows two distinct curves which are indicating the material removal. The black crusts curve begin to rise at a lower fluence value on the x-axis. The sandstone's curve, however, doesn't rise until a much higher fluence value. The horizontal distance between these 2 points on the x-axis represents the safe window of laser energy. Within this window, the laser removes the black crust, but not enough to remove the sandstone underneath. Therefore, the process is clearly self-limiting, because once the crust is gone and the clean stone is exposed, the laser simply reflects off the clean stone without causing damage. For a wavelength like 355 nanometers, the two curves are much closer together. The crust threshold is only slightly lower on the x-axis than the stones. This means it's creating a really narrow safe window. And the process is self-limiting, but because the safe window is so narrow, it is risky. And in the study, they said that they probably would not choose 355 nanometers. And then on the left, we can see the 248 nanometers. And these two curves are extremely similar. They rise at almost the same fluence on the x-axis. There's no safe window. And so then at this wavelength, the stone absorbs energy the same as the crust, meaning that any pulse that will clean the crust will also remove the stone at 248 nanometers. So therefore, this process is not self-limiting. Thus, the conservator's decision is looking at data like this and picking which wavelength will match their goal best. This image shows the laser cleaning's effectiveness on an example Dutch painting. The top image shows that to the naked eye, the painting has obviously been cleaned by using the laser ablation. However, interestingly enough, this is perpetuated on a microscopic level, as the bottom image is even better evidence that the treatment was successful. Shown there is a region of high UV reflectivity, which corresponds to fresher varnishes, showing how all the old varnish has been removed. This validates the precise result of the laser ablation intervention. Today, we've seen how the preservation of art skillfully utilizes impulse and momentum. From examples ranging from the yellow varnish of a Van Gogh to the black crust on centuries-old stone, the challenge has always been how to have enough momentum to remove the surface grime without harming the original beneath. Laser ablation has transformed art restoration into a precise science. The laser pulse, acting over nanoseconds, creates an impulse that creates a change in momentum in the particles of grime or varnish. The selected wavelength and time period allows the particles to gain enough momentum to be ejected while the artwork is preserved. The critical concept is the safe window, where the surface grime's ablation threshold is lower than the artwork's, guaranteeing that the laser's impulse will only ever be absorbed by the top layer. In conclusion, using physics, now the Van Gogh is Van Clean. Thank you.